Okay, so we have considered the S matrix for QED, and then we looked into all the terms in first order as well as in second order in E, and then we looked at various physical processes, and then we discussed which term in the S matrix will contribute to what physical process and so on. We also have seen that there can be more than one term which can contribute to a given physical process, and each of these terms can actually in fact be represented in terms of the so called Feynman diagrams. So, for example, suppose you consider a process like Compton scattering, let us say E plus gamma going to E minus plus gamma going to E minus plus gamma, then there are two terms in the S matrix which gives non-zero contribution to this process at second order, and these two terms are represented by the following two Feynman diagrams. So, you have an incoming electron and you have an incoming photon, and then you have an outgoing electron and you have an outgoing photon at x1, or you can also have an electron E minus which emits a photon at x2, and there is an Fermion propagator between x1 and x2, and the incoming photon is absorbed at this space time point x1. Finally, there is an outgoing electron. So, these are the two possibilities, and correspondingly there are two terms in the S matrix which gives non-zero contribution for this physical process, and these are the two Feynman diagrams for the two terms in the S matrix. What we need to do is we actually need to consider the S matrix, the relevant terms in the S matrix for this process, and then we have to compute the amplitude for this process. So, you have some initial state given by this incoming electron and photon, and you have outgoing state represented by some outgoing electron and outgoing photon, and you know what are the terms in the S matrix for second order. You need to compute this amplitude in order to know what is the cross section or anything you want to do in quantum field theory. You need to evaluate this amplitude. What we will do now is we will formulate a set of rules to get this amplitude, so that you do not have to evaluate it again and again every time you want to compute this amplitude. So we will get a simplified form for this amplitude from what are known as the Feynman rules. We will derive the Feynman rules for QED, and then you can write down this amplitude using Feynman rules instead of working out at each and every time whenever you need it. So this is what we will be doing in today's lecture. Let us first summarize the useful expressions that will be needed in this lecture. We will require the mode expansion for the photon field, which is given by d cube k over 2 pi cube 2 k 0 sum over the polarizations lambda going to 0 to 3 a lambda k epsilon lambda mu of k e to the power minus I k dot x plus a lambda dagger of k epsilon mu lambda star of k e to the power I k dot x. Then we have the Dirac field psi of x, which is given by dqp over 2 pi cube m over p0 is the normalization I have chosen, and sum over the spins CSK USK e to the power minus CSP USP e to the power minus I p dot x, then ds dagger of p VSP e to the power I p dot x. Correspondingly, we have psi bar of x, which is given by dqp over 2 pi cube m over p0 sum over s cs dagger p us bar of p e to the power I p dot x plus dsp vs bar of p e to the power minus I p dot x. And these operators A's and C's and D's, they obey the following commutation and anti-commutation relations. A lambda of k, a lambda prime dagger of k prime commutator is given by minus eta lambda lambda prime 2 pi cube 2 k0 delta k minus k prime, whereas CR k CS dagger k prime anti-commutator is given by delta RS 2 pi cube k0 over m delta k minus k prime, which is also same as the commutator of ds dr k ds dagger k prime, and all other commutators and anti-commutators relating to the fermionic and bosonic operators vanish. So, these are the non-vanishing commutation and anti-commutation relations. So, what we will now do is we will look at the first order term in the S matrix that I will call as S, that I have denoted as S1, which is IE times d4x normal order product of psi bar of x a slash of x psi of x, and we will look at a physical process for which this might give a non-zero amplitude, although we will see later that there is no physical process to which this one gives a non-zero contribution, and then we will evaluate the amplitude for this process in detail. So, let us consider this process of E minus going to E minus plus gamma. This is one possibility, because you can have this term, for example, can contain one term which is a psi bar minus of x gamma mu a mu minus of x psi plus of x. One of the terms in this normal ordering is given by this, and this represents, this psi plus represents annihilation of an electron at x, whereas a mu minus and psi bar minus represents emission of or creation of an electron at the space time point x. So, if this is x, then an electron is annihilated here, and a photon, an outgoing photon and an outgoing electron are created at x. So, this process, this is the term in S matrix, which can contribute to this process. So, we will consider this process and then we will evaluate. So, S11 I will call I e times this d4x. So, we will take this E minus incoming electron with some momentum p and some polarization s, S11 E minus p prime s prime gamma of k prime lambda prime. So, the point is, suppose you have this incoming electron with momentum p and polarization s going to some outgoing electron of momentum p prime, polarization s prime, and some outgoing photon of momentum k prime and polarization lambda prime, then what is the amplitude for this process? That is what is the question that we would like to ask. So, naturally we need to evaluate what happens when the psi plus acts on these states, okay, and a mu minus acts on these states, and so on. So, this is what we need to know. All right. So, to do that, let's look at first the electron state. Okay. Let's say this represents the state with momentum p and spin s. Therefore, this state for electron is given by Cs dagger of p acting on the vacuum. Okay. Now, what we would like to know, what happens when I consider psi plus of x acting on this state. So, what is psi plus of x? We can look at this expression here. Psi plus of x is given by this term. So, dqp over 2 pi cube, and let us use the integration variable to be k, m over k0 sum over s c s k. Let us denote this dummy variable by r, c r k u r k e to the power minus I k dot x. This one acts on this state, which is given by C s dagger of p acting on the vacuum. Okay. So, what do we get? I can rewrite this term as dqk over 2 pi cube m over k0 sum over r, or this times e to the power minus I k dot x, then you have sum over r u r k c r k c s dagger of p acting on the ground state. I just rearranged the terms in this expression. Now, what I will do is, I will take this term here C r k C s dagger of p. I can rewrite it as the anticommutator of C r k C s dagger p minus C s dagger p C r k. Okay. Now, when this whole thing acts on the ground state, this simply means that this and this acting on the ground state. But as you can see, the second term acting on the ground state, there is an annihilation operator. So, when CRK acts on 0 on the vacuum, it gives 0 contribution. So, only thing that is left is the anti-commutator of CRK, CS dagger P, but the anti-commutator we know what it is. This is nothing but delta RS up to some normalization, this is delta RS and delta K minus P. So, we can just substitute that, we can say that this is equal to the anti-commutator of these two operators acting on the ground state, and we will put the known value for the anti-commutator, which is nothing but dqk over 2 pi cube m over k0 e to the power minus I k dot x sum over r u r k, then 2 pi cube k0 over m delta rs delta k minus p. All right. This acting on the ground state. So, the sum over r I can evaluate, and also I can evaluate the integration over dqk. That will give me simply this 2 pi cube and k0 over m, they will cancel each other. So, what is left is us p e to the power minus I p dot x acting on the ground state. All right. So, therefore, what we saw is that from these results, psi plus of x acting on E minus, which is nothing but psi plus x CS dagger P on the ground state is equal to US P e to the power minus I P dot x acting on the ground state. Similarly, you can evaluate what happens when mu plus acts on a one photon state. So, let us say that you have a photon gamma of polarization lambda and momentum k, and you want to know what do you get when you consider a mu x acting on that. So, this is nothing but a mu plus x acting on some a lambda dagger of k acting on the ground state. We can substitute the value for a mu plus, which is given by this. So, this is nothing but integration, let us say this is a momentum p dqk over 2 pi cube to k0 sum over lambda a, let us say you are considering sum over lambda prime a lambda prime k epsilon mu lambda prime k e to the power minus I k dot x acting on a lambda dagger k 0. So, let us rearrange the terms. So, this is integration dq k over 2 pi cube to k 0 e to the power minus I k dot x, and then sum over lambda prime epsilon mu lambda prime k a lambda prime k a lambda dagger p. Again you can write this term as commutator of a lambda prime k and a lambda prime dagger minus a torr which annihilates when acting on the ground state. Therefore, I will just substitute the commutator of a lambda prime and a lambda dagger in this place, and we know what this commutator is. This is nothing but 2 pi q 2 k 0 delta k minus p times minus eta lambda lambda prime. Okay. So, you can now carry out the k integration. When you carry out the k integration, of course, this 2 pi q 2 k 0 will cancel, and what you are left with is minus eta lambda lambda prime epsilon mu lambda prime p acting on the ground state where there is a sum over lambda prime which runs from 0 to 3. Thank you. So, this times e to the power minus I p dot x. Now, suppose you are considering a transverse photon here, okay. Then for transverse photon you can just consider this to be minus delta lambda lambda prime, and what you will get is this whole thing is equal to e to the power minus I p dot x epsilon mu lambda p times the ground state for so if you have the photon with a transverse polarization, then this is what you are going to get. So, let me summarize it here. This is what you will get for electron, and for photons you will get a mu plus x gamma equal to e to the power minus I p dot x epsilon mu lambda p and the ground state. So, we will now use these two results and their conjugates to evaluate the amplitude for this process A minus going to A minus plus gamma. So, let us do that. So, what we need is we have an outgoing electron of momentum p prime and polarization s, and you have an outgoing photon of momentum, let us say k prime, and polarization lambda. This is what we have. So, we have already seen which term in this matrix that may give a non-zero contribution. Let us see minus p prime s prime gamma of k prime lambda and I e times integration d4 x psi bar minus of x gamma mu a mu minus of x psi plus of x acting on E minus Ps. Okay. So this part I can directly substitute it here, and this one, as you can see, psi bar minus acting on this will give me, from this term itself I can conclude that if I have an electron state E minus of p prime s prime, if psi bar minus of x acts on it from right, then this will give me 0 times us bar of p e to the power I p dot x. P prime, thank you, P prime and S prime. All right. Similarly, I have, if a mu of x, a mu plus x acts on this state, then what I will get here is I e integration d4 x. Then these are numbers as far as the ground state is associated, because these are the operators which acts on the ground state, but these numbers simply multiply them. So I can just take these things out here. Okay. As far as this state is concerned, these are just some multiplicative coefficients. So this is just 0 0, which I will normalize the ground state to be 1. Then all that is left with is u bar s prime of p prime e to the power I p prime dot x, and then gamma mu. Then when a mu minus acts on this, what I have is e to the power I k prime dot x and epsilon mu lambda k prime, and then this one is just us p e to the power minus I p dot x. Okay. Sorry. Epsilon star. So let's consider the photon to be all transverse and real. Okay. So you are right. This in principle should have a star, but I will not. I will assume from now on that all the incoming outgoing photons are represented by real polarizations which are transverse. So what I have is I e d4 x e to the power I p prime plus k prime minus p dot x, and then you have us prime bar p prime gamma mu epsilon mu lambda k prime us of p. This quantity I will call this to be, so I e times this quantity I will represent it by m, which I will call as the Feynman amplitude. So what I get is 2 pi 4th delta, the 4-dimensional delta function p prime plus k prime minus p times m, where m s prime s, where m is I e times u bar p prime epsilon slash lambda of k prime u p. Okay. So, this is what I get for this amplitude, but now we will see, because this delta function is there, whether it can actually be satisfied for this process. So, this is what is imposed by the delta function. It p prime plus k prime should actually be equal to p. Therefore, p0 will have to be equal to p0 prime plus k0 prime, or since p0 is the energy of the electron, it's nothing but mod p square plus m square should be equal to square root of mod p prime square plus m square plus mod k0 is simply mod k prime, because photon is massless. What about the ith component of the momentum? P prime plus k prime is equal to p. Now, since the incoming electron is a massive particle, you can go to the rest frame of the incoming electron, and then you can do this calculation here. So, in the rest frame of the incoming electron, p equal to 0. Therefore, in the rest frame, p prime is equal to minus k prime. Now, what this equation gives me in the rest frame? This gives me, so the RHS is simply equal to mod p prime square plus m square plus mod p prime. This quantity is, as you can see, this must be greater than or equal to m, and the equality will be saturated. This inequality is saturated only when p prime is equal to 0. So, therefore, this will be satisfied only when p prime and k prime is equal to 0, or in other words, when there is no outgoing photon at all. For k prime non-zero, this will not be satisfied. Therefore, this delta function, because of the delta function, this amplitude is always 0 for any for any outgoing real photon. So, you can try to consider other possibilities in the S matrix, and you can see that this first order term does not give any contribution at all, because you will always get a delta function like that, and then you will see that it will never be satisfied at all. So, there is no physical process to which the first order term in the S matrix gives any contribution. Now, what we will do is, we will consider a simple example at the second order. Let us consider the example of Compton scattering. So, in the case of Compton scattering, we have E minus plus gamma going to E minus plus gamma, and we saw that at the second order there are two terms which can contribute. So, S2 E minus plus gamma going to E minus plus gamma has two terms which I will call as SA plus SB, where SA is equal to minus E square d4 x1 d4 x2 psi bar minus x1 gamma alpha ISF x1 minus x2 gamma beta psi plus of x2 and SB is minus E square d4 x1 d4 x2, then psi bar minus x1 gamma alpha ISF x1 minus x2 gamma beta psi plus x2 times A beta minus of x2 A alpha plus of x1. This is what we will get. All right. Strictly speaking, because there is a normal ordering, I should have written it here, but it does not matter because this A minus commutes with psi plus. Same thing here. And there are two diagrams which actually contributes to these two processes. One of them is given by there is an incoming photon and there is an outgoing photon at x2, x1. This is gamma, this is A minus, A minus. The other one is there is an outgoing photon at x2, E minus, and there is the incoming photon is observed at x1. These are the two processes, physical processes. So, what we need to do is we need to consider the in state, which has one electron and one photon, and the out state or final state F again has one electron and one photon. We need to consider the spin and the polarization and momentum of all the photon as well as the electron in initial and final state, and we need to consider, we need to find what is the amplitude for this process, what is F S A I and what is F S B I. These two matrix elements we need to consider, and we need to take the sum of these two matrix elements to compute the amplitude for this process at lowest order. So, let us evaluate first this quantity here. We already know what we get when psi plus acts on the initial state and so on. So, let us do that and see what we get for this amplitude. So, I will write F S A I, this is minus E square d4 x1 d4 x2, and then so this initial state here I again has some electron of momentum P, and polarization I will call this to be S, and it has a photon of momentum k and polarization lambda. This I can take as E minus P s and gamma k lambda, and this state, the psi plus will act on this one, whereas the A plus will act on this state here, right. So, therefore, what I can do is I can just consider the inner product E minus P prime. Let us suppress the spin index for the moment. We will keep track of the spin indices later on. Psi bar minus x1 gamma alpha I S f x1 minus x2 for the fermion propagator, then gamma beta psi plus of x2. This acts on the incoming electron which has momentum p and spin s. This times the photon of momentum k prime A alpha minus x1 A beta plus x2 acting on the photon state of momentum k. Okay. So what is this? This we already know. We have evaluated this piece, we have evaluated this piece, we have evaluated this one and as well as this one. So all these things we already know. So we can put all these things together and then we see what we get. So let us do that, and finally what I will do is that this fermion propagator I can write it in terms of its Fourier component. So this quantity is minus E square d4 x1 d4 x2, and then this will give me, as we have already seen, u bar of p prime e to the power I p prime dot x1, okay, and then this one gamma alpha, this one in terms of its Fourier component is given by 1 over 2 pi 4th integration d4 q I S f q times e to the power minus I q dot x2 minus x1. You will see very quickly why I wanted to write it this way, and then I have gamma beta and then psi plus acting on E minus will give me u p e to the power minus I p dot x2. Then finally I have this, which is nothing but epsilon alpha of k prime. I am suppressing the spin as well as the polarization indices, e to the power I k prime dot x1 and epsilon beta of k e to the power minus I k dot x2. That is all I have. So let us rearrange all these terms and then see what do we get. What I will do is that I will collect the coefficients of e to the power. So I will put all these exponential terms together. I will write it in terms of two terms. One, collecting the coefficients of x1, and then I will carry out the x1 integration here. Then the second exponential, I will also again I will carry out the second integration. So this is nothing but minus e square d4 x1, d4 x2, and then d4 q over 2 pi fourth, and finally e to the power I p prime minus q plus k prime dot x1 e to the power minus I p minus q plus k dot x2, and u bar of p prime epsilon slash of k prime I SF q epsilon slash k u of p. So as you can see, you have e to the power I p prime dot x1, e to the power I k prime dot x1, and then e to the power. So let's write it as a plus, and then e to the power minus I q dot x1 here. Whereas in the second term, I have, if I just look at the x2s, I have e to the power I q dot x2, here I minus I p dot x2 and minus I k dot x2. That when I put together I get here, and I took out the q integration outside, and then remember this SF is an operator which is inserted between gamma alpha and gamma beta. So I do not have the freedom of moving it anywhere else. I have to do that, but these epsilon alphas are numbers. So I can write, I can compute this, I can bring this epsilon alpha here. That will give me epsilon slash k prime. So you have this u bar p. This is a number, I just took it outside, but this row is already there. So u bar p, and then gamma alpha epsilon alpha will give me epsilon slash k prime. Then I have SFQ, which is here, and finally I have again this gamma beta. I can take this number epsilon beta k, that will give me epsilon slash k, and finally I have UP. Remember, I do not have the freedom to move these things anywhere other than where they are. Of course, I can write them in terms of their components, and finally I can move the components around because they are just numbers, but these are not numbers, so they are there. Now I can carry out the x1 and x2 integration, and also I can carry out the q integration. First, let us carry out the x1 and x2 integration. That will give me two delta functions. Here I get delta p prime minus q plus k prime. Here I will get delta p minus q plus k, and when I integrate out over q, I will get delta p prime plus k prime, p prime plus k prime minus p plus k. Okay. So this is what I get, and then there are this factor of 2 pi to the power 4th is here, but when you carry out two x integrations, you will get two factors of 2 pi to the power 4 in the numerator. One of them will cancel with this one, and the remaining is given by 2 pi to the power 4th delta of p plus k minus p prime minus k prime times this quantity minus e square u bar p prime epsilon slash k prime I S f of q is nothing but p plus k epsilon slash of k u p. Okay. So this is what is the Feynman amplitude. So what I did is I evaluated this, and then I wrote it in the form of a delta function times some matrix here. I will do the similar thing for SB, and then finally to get the full amplitude for this process I will add them up. But again I will give you a set of rules, so that just by looking at the Feynman diagrams you can evaluate this matrix element here instead of going through all these algebras, which we will do in the next lecture.